Okay. Welcome to the DDPS seminar, everyone. Before I introduce today's speaker, let me go over some rules and logistics. First of all, please mute yourself during the talk. But if you have questions, you can unmute and ask questions, or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Let me briefly introduce our speaker today. It's a great honor to host Professor Max Welling, who is a full professor and research chair in machine learning at the University of Amsterdam, and a Merkin Distinguished Visiting Professor at Caltech. He is co-founder and a co-founder of the startup Cusp AI in materials design. He's a fellow at the Canadian Institute for Advanced Research and the European Lab for Learning and Intelligence Systems, where he served on the founding board. His previous appointment includes partner and VP at Microsoft Research and VP at Qualcomm Technology, professor at UC Irvine. And he finished his PhD in theoretical high energy physics under supervision of Nobel Prize winner Professor Gerald, right? And he then switched fields to focus on machine learning, first as a postdoc at Caltech under supervision of Professor Kerito Perona, and then a postdoc under supervision of another Nobel Prize winner, Professor Jeffrey Hinton at UCL and the UC Toronto. Today, Max will talk about is AI shifting the paradigm of scientific discovery. I'm sure we are going to hear a wonderful talk today. Now let me ask informal questions and then move on to fun part. So today's informal question is, Max, I know that as I introduced today, you've been studying the physics first, right? And then somehow move on to the machine learning. And you must be fascinated by some aspect of the machine learning. That's why you transitioned from physics to the machine learning. If you can tell us briefly about how that transition happens, that would be awesome.
Yeah, thank you very much for the introduction. Young-Soo, I'm happy to be here. I think we have people online which are not muted, so I'm sure. So indeed, so I did my PhD in two-dimensional quantum gravity, and I didn't quite see that's going to make the impact in the world. And so I wanted to do something where I would more impact. And so machine learning was at that point a budding field with maybe people training models with a few tens to hundreds of parameters, not trillions as we do now. And so I started working on that. And that's also the reason ultimately why I started startups like Cusp AI, which is to make an actual real impact and not just a theoretical impact with papers. I'll talk about that a little bit today. But ironically, I've gone full circle, going back to physics, material science, but also I'm very interested in quantum mechanics, actually the fundamentals of quantum mechanics and quantum computing. So I won't talk about that, but today I'll talk about machine learning for molecules and materials. So I'll start my talk by talking about two revolutions which have happened over the course of humanity. Not the first one, but the very impactful one was the Industrial Revolution, where human labor was being replaced by machine labor. And it was, of course, it resulted in what we have today, but including all the pollution that this generated, because we needed to drill for oil and gas and other fossil fuels in order to power that revolution. And it's that which is currently...
Oh, sorry.
I don't know why. Sorry. Sorry, we have a little technical difficulty. Oh, there we go back. That's already good. So we need to power that revolution with fossil fuels, which ultimately also caused the a large amount of carbon dioxide in the atmosphere at this point. And so now, today, we are looking at an information revolution, which is replacing mental human labor by machine mental labor, if you wish, which is, of course, the AI revolution. And the hope is that maybe the AI revolution could help also clean up the mess from the previous revolution. So here's a little graph, which is the carbon dioxide levels in the atmosphere. This is 1764, which is the invention of the steam engine, and the levels of carbon dioxide and global temperature, in fact, but not shown here, are rising right after that. This is my birth year. So in some sense, our generation, I'd say my generation, has been benefiting from the fact that we can dig up fossil fuels and use them. And it's also up to us, I feel, to hand over the world to the next generation in a more clean state, which is we need to start removing carbon dioxide from the atmosphere, which is a technology that currently doesn't really exist at the scale that we need it. So here's a graph which shows some scenarios which are necessary to stay within 1.5 to 2 degrees. It seems we're already at 1.5, by the way, but let's say 2 or 1.5 degrees global warming, which means that we have to decrease the amount of emissions in the atmosphere. And by 2050, we need to be completely carbon neutral under all of these scenarios. Now, I would say these scenarios should go down in carbon dioxide under, I would say currently the way the world is moving. I don't see this coming down at all. So it will hopefully be a more sharp peak at some point. But we will have to be carbon neutral at 2050. But after that, and this is basically replacing sort of fossil fuel with sustainable energy sources. But after that, there is a century, or at least half a century, but more like a century, of having to remove carbon dioxide from the atmosphere at half the rate that we're putting it in now. That technology at that scale does absolutely not exist, but all of these scenarios count on it. And so that needs to be developed, in my view, in order to not go into crazy global warming. And so the hope is that technology and AI can help us achieve that. And so I think we are at the cusp of somewhat of a revolution in AI, using AI in the sciences, and of course in this lab. People realize that if I look at all these photos here, which are all about how AI will help change, scientific simulation and stuff like that. So you're all into this, I'm sure. So I sort of identified 2 steps for this to happen, or these are basically happening right now. The first step is to replace pieces and bits and pieces of experiment to computer simulation. So experiments are expensive and slow. And the more you can do in a computer, the faster you can go through design cycles and all that. So of course the compute is growing exponentially, and that's good. And so we are going from basically just trial and error in experiments to doing lots of experiments and storing the data, analyzing it maybe with statistics and machine learning techniques, to a state where we do all the simulations of the molecules, literally the actual simulation of the molecule in silico. So that's the first step. And then the second step is going from simulation to emulation. So here's an example in fluid dynamics. So you're a car designer, you test your car in a wind tunnel. Now you've already made the first transition, so you're not testing it in a real wind tunnel, but you're doing it in a digital wind tunnel. And then when you design your next car, instead of just redoing that process and just going through the same expensive simulation, you could have stored the data from the first one, then trained a neural network to either accelerate this particular simulation or actually directly predict the relevant properties. In other words, machine learning is providing a shortcut for these kinds of simulations. And of course, one big challenge is to do it in a reliable way, so that you will actually also, if you go slightly out of the domain, that you will have reliable predictions. And so, this kind of revolution is happening across all the scales of scientific research, all the way in particle physics, where you talk about picometers and femtoseconds, all the way up to astrophysics, where you talk about light years and gigayears. Now in this talk, I'll be touching on 2 of these, but I acknowledge this is just a small slice of where what you can do. The first one is simulating molecules, and the second one is something about simulating fluids. First, a little bit about molecules. Why am I very interested in molecules? Well, they are basically the root of everything. If you can simulate and control molecules, you can solve a lot of society's biggest problems. Of course, drug discovery is one, photocells is another. Better lubricants, 20% of all our energy losses seem to be due to friction, so better lubricants can help there. Better catalysts, which are of course underneath all chemical reactions. And then, here's a process like nitrogen fixation for fertilizers, and carbon capture, which you just mentioned, which is also really important. Okay, so now what are the challenges in molecular simulation? I'll first talk a little bit about molecular simulation. So what are the challenges in molecular simulation? So a molecule, at a very rough, sort of sketchy sort of level is a bunch of atoms or ions connected by bonds, plus a electron cloud around it.
I do have a clicker, but it's I cannot
Okay, it's
plug
fine.
in.
Now, what are the three challenges for molecular simulation? So the first one is basically, in order to evolve a molecule forward in time, it's just, in principle, we think Newtonian dynamics, which is that the change in position is given by velocity, and the change in velocity is given by force. The first problem appears because the force is largely quantum mechanical due to the electrons, right? So this gives you a very hard computation to do if you don't approximate it. The second one is this is a highly chaotic system. It's a highly nonlinear set of equations, set of ODEs, if you wish, that needs to be evolved, and very quickly, of course, this becomes chaotic. And the third one is if you want to design materials, the search space is humongous. 10 to the 60 at least, but possibly larger. And so how do you effectively search through the space of molecules and materials? Now here's a few examples of things I've worked at, but also where the field sort of has started to make contributions. And so on this side, we have the time-dependent Schrödinger equation, where the green blob is the sort of electron cloud. This is a beautiful visualization by Quantum Magazine. And so here's a time-dependent Schrödinger equation, and then we have, ideas to take the functional for a DFT, which is a functional of the density, the electron density, and you have to write down something for that. And now people have started to train machine learning models for this DFT functional. And the other one is quantum variational Monte Carlo, which is another technique for solving this equation. And people have also started to use neural networks in quantum variational Monte Carlo. And the examples of that are FermiNet and PolyNet. At one level up, we actually do Langevin dynamics. This is water being simulated. And you use the Langevin equation for that, which is again, Newton dynamics. Change in position is velocity. Change in velocity is given by a friction term, and a force term, and then random noise. And it's this term which is hard, and people have started to build neural networks to replace their quantum mechanical calculation, or you typically do it with a DFT calculation. And that's called the machine learning force field, and I'll say a little bit more next. So this is something I hope also to have some time to talk to you about. This is DFT, but for thermodynamics. So it's a DFT calculator method, which is an almost perfect analogy of the DFT for quantum mechanics, but then for thermodynamics. Again, you have to write down a functional. You don't know what the functional is. And because people have written down rather simple things, these methods didn't work very well. But now you stick in a neural network, and now it starts to work really well. And I'll show you some results. And then there's, of course, the Navier-Stokes equation for predicting the weather. This is a simple version of it. There's huge amounts of data available for this, which is therefore super, successful place for applying machine learning. And we've trained, when I was at Microsoft, we've trained a large model, Aurora, to predict the future state of the weather by solving it all as a neural network, not even worrying about the physics beneath it. And then there's beautiful applications. So there's models that can generate drug-like molecules in the pockets of a say, protein to develop new drugs. There is the design of new catalysts to accelerate chemical reactions. And quite recently, the paper was published in Nature for the diffusion models for generating materials. This is the paper MatterGen from Microsoft that would just generate materials, and you can prompt them with certain properties, and they will generate these materials for you. So these are all new techniques where machine learning is sort of, I would say, changing or disrupting this field of atomic simulations in search. And so here I've sort of rewritten a little bit, sort of a hierarchy of all the things that people do in the chemistry and physics community, all the way from ab initio electronic structure methods, to molecular simulations, and then coarse graining them, to particle-based simulations, and then coarse graining particle simulations, all the way to classical density functional theory and continuum methods, which is solving PDEs. And for each one of these, there is now a machine learning method that helps improve it, right? Quantum neural Monte Carlo, the quantum DFT, force field methods, and then force fields for all of these, and then classical DFT, where I'll talk about a bit, and these PDE circuit models, which are these methods for weather prediction. And so we are seeing a sort of a real change in this field, where we accelerate the simulation by using machine learning methods. And so now I'll do a quick digression, because I need some concepts to tell you a little bit more about some of these techniques. So the first one is symmetries and how to build them into neural networks. Now, symmetries play an incredibly important role, as you all know, in physics. You can basically derive special relativity from a few simple symmetry arguments, like the Lorentz invariance, and you can derive Maxwell's equations by unifying electricity and magnetism by basically changing frames. So you can turn magnetism into electricity and back by just moving observers and thinking about what observers see. It's a very powerful tool in physics. Even general relativity can be derived from this simple equivalence principle that gravity is sort of the same as, it's exactly the same as acceleration. And even the standard model of particles is governed, of course, by symmetry groups. The different particles are different. Right? You say you can rotate, or you can turn one particle state into another particle state by a symmetry transformation. And that sort of gives you the organization of fundamental particles. So now in neural networks, though, it wasn't very obvious how to use these symmetries, right? So you could train a neural network which would say, predict for me, let's say, the energy and the forces on atoms from, you give it the current state of the atom and you want to predict the forces so you can move it sort of along, you can evolve it. Now, it's clear that if you would rotate a molecule in space, or you would move a molecule in space, it would give you the same energy and it would rotate all the forces. So that's not if you know the first solution, you just know the second one for a rotated frame. The neural network, however, doesn't know about that. So it would consider a molecule input and a rotated molecule input as a completely different new problem, and needs to learn how to produce forces for that. And the output, if you didn't train it long enough or with enough data, might actually not be a perfect rotation. And so with Taco Cohen and Maurice Weiler later and a whole bunch of other students and postdocs, we studied how to take this symmetry principle and put it into a neural net. And the underlying core mathematical idea is this idea of equivariance, which says, here's the equation, but here's the picture. Is that if you take an input image and you translate it, and then you convolve it, or just filter it to get you the first layer of a neural net. That should be the same as first filtering and then translating. If you put constraints, so this closing of this diagram, this commuting of this diagram, will put constraints on what this filter maps can be. So if you restrict your neural network to have this kind of property, then you're guaranteed that whatever you do at the end has the symmetry property of the group that you're interested in. And so if you're interested in that, this is an excellent book written by Maurice and other co-authors, but mostly by Maurice, I would say. He has beautifully not just written the book in sort of a hierarchical fashion where the first chapter is very high level and then it goes into deeper and deeper levels, but it's also very richly and beautifully illustrated. So this is the perfect introduction into this field if you're interested in learning more about this. And so we also worked on graph neural networks because obviously an image is a regular, you can represent as a regular grid, but a molecule isn't nicely represented as a regular grid. It's more like a graph where the atoms are the nodes and then the interactions are at the edges of the graph. The only problem is that it's not so clear how to do a convolution on a graph. This has to do with the fact that in a graph, if I just move a particular node, drag it to some other place and change the order, the convolution shouldn't change, but the representation, if you don't take the right representation, it will change. And also, it should be able to handle an arbitrary number of neighbors, not just a fixed number like in a regular grid. And so with Thomas Kipf, actually, first we developed this idea of a graph neural network that is able to send these messages in these graphs, so to do a convolution on a graph. And then later with Victor and Emil, we also turned this into sort of a more an equivariant version of that. So now here you have a graph, you do your message passing on the graph, or message passing or convolution if you wish, then you rotate the molecule. And so now this thing is, if you do message passing and rotate the molecule, it should give you the same as rotating the molecule and then do the message passing. And so now you have an equivariant model for graph convolutions on, that is fully equivariant and therefore appropriate for modeling molecules. These are a bunch of equations, so just to show this actually doesn't have to be complicated. So running these equations to get this to be equivariant doesn't have to be complicated. So here's two papers that we wrote, among others, about how to take that idea and turn this into a force field. Right? So this is the SE3 transformer, which is a model that was actually used by David Baker in his work on proteins, or zetafold, and something similar was in the first versions of AlphaFold. And then another one, steerable equivariant message passing for force fields. And so these methods are completely equivariant, and basically that means that if you rotate in the frame or you rotate the molecule, nothing changes. And so what you see here is over time passing messages, and these are spherical harmonics representations visualized as you're sort of sending these messages over the graph. And now the nice thing is that these machine learning force fields, they sit between ab initio DFT calculations to do the forces, which are very expensive, so you can only do very small molecules, and classical force fields, which are inaccurate, but you can do large molecules. And so this machine learning force fields are sort of starting to span this field. So they can do large molecules, but also at the level of DFT accuracy. And there's quite a few efforts around, also in big tech companies, to build these basically foundation models for these force fields, which should work across a large swath of chemical space. And of course, maybe the main example of why this field is booming is the fact that the Nobel Prize was awarded to chemists or biologists, computational chemists and biologists who have both solved the problem or sort of made a huge amount of progress on the problem of going from sequence to three-dimensional structure, which is AlphaFold, of course, or take the structure and design the sequence that would have that structure, which would be a design problem. And so, I think this year's Nobel Prize is a clear sign that this is an important field that will deliver a lot of interesting results. Okay, so that's for molecular science, and I will discuss a few more things later in a little bit more detail. There's this other field which is also being disrupted or going very strong with machine learning, which is PDE solving. And it started, this paper by Stephen Hoyer and a whole bunch of other co-authors, by basically taking a usual solver and starting to look at places where you can replace certain bits and pieces of it, stencils, for instance, with machine learned stencils. So you could just learn your own stencils to solve this equation, but otherwise you'll keep the solver the same. You just keep the same solver, but just improve some of the pieces of it. And slowly that evolved into things which were starting to remove more and more of the physics. And in particular in fields where there's lots of data, you can afford to remove the physics. And so there's these deep operator networks, and then there's neural Fourier operators. These are all examples of basically removing the physics and just training a model that maps into some latent space, evolves the system in latent space as a recurrent neural network, and then predicts back the next state. Now there's also attempts, of course, to try to bring back some of the physics, and this is this pin structure physics, fork neural networks, where the actual equations of motion and the possibly boundary conditions can all be enforced as regularizers on these solvers. So again, so it's a very fast evolving field. Here's some of our own contributions in this field. This is a GNN model where basically you can have an irregular grid. You first encode for every node in the grid, you encode a feature vector or token. You put them on the grid, then you send messages across the grid, which makes all the nodes to communicate with each other, and then you do a final smoothing using CNN to predict the next state of the original model. And this we could train quite successfully on irregular grids. Now it's fun to think about symmetries here too, as we did for neural networks. It's a bit harder to actually include them as full equivariant solvers. But one thing that we could do is we could study, for a particular PDE, we could study the symmetries. In fact, it's a fully solved problem. So you can just, the lead point symmetries, you can actually just run a piece of software, you get all the symmetries out for a PDE, which I didn't know, but it's kind of beautiful. So you know all these kind of generators for each one of the symmetries. You can then represent the group as a product of these generators sort of strung together. And then basically what we did is we took original data and we started to enhance the data set by applying all of these symmetries. So you get for free basically data enhancement. And then you can solve this, you can train solvers with much less actual data than you could before. Now, I guess there's some big successes here already going down to maybe 2016 or something. This was one of the first papers by NVIDIA group where it was called ForecastNet, is a model that already globally solved or sort of predicted the next state of the weather like 10 days ahead or something like this with these neural Fourier operators. And then Quangle weather came slightly after that. These are all solutions which are completely based on machine learning. There's no physics in the actual equations. And then there's GraphCastNet, which is a model based on message passing, on a sort of hierarchical multi-scale graph, and this is a DeepMind paper. So the contribution we made in this field was called Aurora. So the change, what did we do in Aurora that was different than before? So it was made so that the encoder could take absolutely any kind of data. So it could take data from the US at very high resolution but local. It could take global but much more coarse data. It could take all sorts of other data in. It would embed all of that into a latent structure, and then basically a transformer-based encoder, and then evolve that and decode. So the data set is about over 1 million hours of data. It was trained on about 38 or something A100 GPUs for, I don't know, a few weeks, so not too terrible in that sense. It achieved 5,000 times speed up relative to the normal solver. So that's the big gain you get. You can solve things 5,000 to sometimes 10,000 times faster than the original solvers can. All right, and then so what this particular model could do that other models couldn't do was, besides predicting the usual hydrodynamic variables like wind speeds and temperature, it could also predict things like air pollution, concentrating greenhouse gases, etc. So by just actually keeping the encoders the same and just fine-tuning the models based on new data slightly. And so it could produce air pollution with very high quality. And what's also interesting is that sort of the standard ways, sort of the simulators for sort of weather prediction is IFS HRAS, which you see here, and lower is better on these curves for this is surface temperature and that's wind speed. These machine learning models actually do better than numerical solvers. And you can just wonder, well, how is that possible? Since they're largely trained on maybe data also from the simulators, but in this case, of course, there's also real weather data that's being included into these models, and this real weather data can actually make it better than the numerical solvers can, and much faster. So I think that would count as a true change in the field. I've seen meteorologists from highly skeptical change to, oh right, we really need to do something with this because this is actually changing our field. And then I'll talk a little bit about some other applications of where AI has been helping sort of the sciences and also in the other direction, right? So I've used symmetries to improve neural networks, and here physics like non-equilibrium thermodynamics is also helping build better generative models. And so I would say the causal arrow goes in both directions. And so in 2013, Dirk Kingman and I developed this variational autoencoder model. And that's a model where you take a distribution of data and you map it into some latent space. And then that's the encoder, which is sort of, this is your semantic representation if you wish. And then there's a decoder which samples from hopefully something very close to that particular sort of embedded manifold. And then inverts the encoder into basically sampling back from a distribution which is then approximation to the original data manifold. But it did so in one stochastic step. So it was a complicated neural network, but then noise was only added at the end. And so that evolved into these kind of diffusion-like models where people don't train the encoder, so we train the encoder. The encoder is fixed, it's just some fixed process, like a Ornstein-Uhlenbeck process. But you have many stochastic layers, which gives you embeddings which are not structured at all, they're just completely mixed, which you can very powerfully train to invert them. And so you can see here an example, like a two-dimensional example, you have a data manifold, it gets kind of diffused into sort of a blurry blob. And so if you look at every data, so it's like a process where you can sort of increase entropy, right? And then this is a physical process if you want. And then you're trying to invert that. So you're trying to go from this blob and generate back the manifold. Basically by training velocity fields. For every point in space you train a velocity field, which is now a neural net. And it says, if you're here in this space, follow this velocity field. And then it just put things back onto this manifold. And by doing this slowly, step for step, you can really train very powerful models that get you from there to there. And these authors already acknowledge that that is actually an application of ideas of non-equilibrium thermodynamics. And that's a field that is really developing. And writing a book about that, I'll share a little bit more later. Because these connections between machine learning and thermodynamics are very, very deep, actually, in my view. So I would say that the next step in this development was to map the problem from a discrete problem to a continuous problem, an SDE governed by Brownian motion. People know how to invert that as a long-run result. You pick up this extra term, which is it's a very non-physical process, obviously, because you go against the second law of thermodynamics, but mathematically you know how to invert it. You pick up this term, but it's kind of funny because it depends on the actual density itself. And you don't know it, but the machine learning model will train this. So you train the model to approximate that score function, and then you can run the process in reverse to generate images. So here's a few equations then. So there's a very interesting deep relationship between machine learning and thermodynamics. So I guess most of us are physicists here, or mathematicians, or chemists, or something like this. So you're probably very used to these types of equations, right? This is saying if you're in equilibrium, you have a Hamiltonian that describes your system, and you have a temperature that's connected to the heat bath, then the distribution of your latent variables is actually a Boltzmann distribution, right? Where x might be microscopic variables you observe, like maybe the volume in which everything sits or something like that. And z are the microscopic degrees of freedom of the atoms. That's the equilibrium distribution, that's the Boltzmann distribution. And so you can write down a free energy, which is minus t, like the log partition function, which you can lower upper bound by a variational free energy with a variational distribution Q. And that's given by the expectation of the Hamiltonian under that Q minus temperature times the entropy of that Q. Now, if you relax the system, if you kick it out of equilibrium, right, then Q changes, H doesn't change, and you relax it back to equilibrium, then you minimize this variational free energy. And when Q becomes the Boltzmann distribution, you're back to the free energy, the minimum, the free energy described by the log partition function. So work is related in this view by changing this free energy by changing the Hamiltonian. If you start changing the Hamiltonian around by applying forces, then you're performing work on the system. And the second law of thermodynamics follows from the fact that if you relax this system, then you will find that always the entropy of the system and the entropy of the bath, which is given by basically the heat you're generating in relaxing the system back to equilibrium, the sum of those two will always be positive on average, not for any path, but on average with very high likelihood, that's going to be positive, and that is the second law of thermodynamics, basically. If we go to the machine learning side, we typically write in posterior distribution. We use Bayes' rule, so we say we have some observation x, we have latent variable z, which could be the latent variable of some embedding, and we know by Bayes' rule that's given by the joint divided by the marginal px. And then you can write down a free energy, which was done by Jeff Hinton and Redford Neal a while ago. You can write down a free energy as minus log of p, which is the probability of x, of the data, and you can upper bound that by the variational free energy, again with some variational distribution q, and it's given by the the expected value over q of minus log p, the joint, minus the entropy, right? And if you compare it with this, you can just read out that h is minus log p of the joint, and the temperature has to be set to 0 because there's no real heat path in this case, and there's q. And here we have a famous algorithm, which is called the expectation maximization algorithm from statistics, which says if I want to learn a system, I need to do two things. I need to change the model P by changing the parameters, right? That's the M step, and that's performing work because now you're changing the Hamiltonian. And the other step is relaxing the system by changing Q back to equilibrium, which is what we call inference in these models. And that's equal to the basically execution of the second law of thermodynamics. So these two things match perfectly with each other, and they're the same. And the claim is that the mathematics underlying machine learning, probabilistic machine learning and graphical models is exactly the same language of non-equilibrium thermodynamics. And that means there's a lot of very interesting results we can import from non-equilibrium thermodynamics, like fluctuation theorems and all these kinds of things. Okay, so here's sort of a mapping of what's been happening recently in the machine learning field. And my claim is basically all around free energy. There is variational inference and machine learning and MCMC sampling. Those are inference algorithms. There is reinforcement learning and optimal control algorithms. There's Schrödinger bridges and optimal transport. There's more mathematical sort of concepts, but they're being used a lot in the machine learning community recently. And then there's generative models like diffusion models and normalizing flows. And all of these can be understood by writing down a free energy of this kind, plus assuming that we have Markov chains over the latent variables. So we have a generative process that runs backward in time, if you wish. It runs against the second law of thermodynamics. It's like the unscrambling of an omelette. Right? You start with you're picking it from a prior and then moving back to produce things which have very low entropy. And this is the forward process where you start from a data point and you slowly deconstruct it by adding noise. If you take these assumptions, then all of these things you can understand this as basically non-equilibrium thermodynamics. And I'll talk about a few of these. So clearly, the diffusion model in one direction goes from an actual structured object and destroys it into a blob of noise, right? So that is entropy production. Basically, that's a physical process, if you wish. Unfortunately, that's the physical direction. We all disintegrate at some point. But what we want is going in the opposite direction, right? By putting in energy and trying to construct structure out of noise. And that's what these generative models do. They go in the opposite direction of the second law. And surprisingly, of course, by that kind of thing, you can actually generate images like this, and they're becoming scarily good these days. It's an extremely powerful tool. But we have also used that to generate molecules. You can use exactly the same idea and say, I want a molecule with these properties. Now, train a model that can do that from data, also the simulated data, and then you can generate, so this is a real process that we've trained, we can generate these molecules with these properties. And MatterGen is now a version of that actually generates materials. So that idea was also used by us, and especially by these two students here at EPFL, to generate drug-like molecules in the pocket of a protein. Right? So you say, this is the pocket of a protein, has this shape. In fact, I have a few components, maybe anchors, which I want to, in particular places, complete the molecule so that it will actually fit in the pocket and has the properties that I want. And so this is a very early version of that. This idea has also evolved already quite a lot. Then we look a little bit at optimal control and Schrodinger bridges. So this project I call Project Sisyphus. This is this poor guy that had to roll a rock up a mountain, and then exactly when he was there, it would always roll back and he would start again. We all Greek mythology. So that's kind of the fate of a molecule when it's trying to sample and go from one metastable state to another metastable state. If you try to do this by molecular dynamics in your computer, it will take insanely long, like the age of the universe 10 times over or something to get there. And so you need to help it a bit. So you need to add an extra force to these atoms so that you can just move it over the energy barrier and get it into the other side. And you can then track it. Of course, it's a very unlikely event, but you can track it, you can study it, and then you can compensate for the fact afterward that you have added all these forces. And so that's called path integral sampling. And so the idea is you have an initial state for your atoms, given by their positions, and now you follow normalized Venn dynamics, but you add an extra control term. The extra control term is nudging the atoms in such a way that you change the conformation or even have a chemical reaction happening at that space. Either you move it over the energy barrier. And that's a reinforcement learning problem because you just give it reward for making that happen in such a way that you do it at the least possible total energy expenditure. And so this is a paper that we produced, and we're still working on similar ideas here, where this is the free energy landscape, this is the conformation of the molecule, and you're driving it, so that it will get to the other local minima. And so here it has to be pushed over the energy barrier, and then it gets into the other local minima. So the energy goes up and then the energy goes down. And now you can study these paths and figure out, how chemical reactions happen and what their rates are, for instance. And then here's an application on free energy. This is a recent paper that just got accepted in PRL. So this is this application where you do density functional theory, but not quantum, but classical. So it's actually a version that doesn't, it's less complicated, but the mathematics follows extremely similar lines. So you write down the grand canonical potential, which is the sort of free energy, but with a particle path. You write down the free energy for the system which only models the internal interactions, so not the interactions with the external potentials. And then there's a separate term which models the interactions with some external potential. Could be a molecule that's fixed, like so if you do adsorption, you want to get a fixed external potential, you want to get lots of molecules which kind of absorb, and a chemical potential. And of course, you have to write down this thing, but it's very complicated because it depends on the properties of your liquid or your gas. And so what we will do now is we'll learn this functional, like some of these approaches in the quantum version as well. We'll learn that functional from MD data. So it's an emulation, right? So you generate lots of data like here, and you train a functional neural network, but within the same framework of this dimensional functional theory. And then once you have that, you can now basically run an algorithm to minimize this for a new external potential. You initialize it some rho, you minimize this functional and get your equilibrium state. And you can even use it to do dynamics, it turns out. And so here's the method that we developed in a little bit more detail. And the big advantage here is that we can train the entire model with setting all external potentials to 0. Why is that nice? Because you can reduce your data set a lot. So the only thing you need is basically this radial distribution function, which says, if you're at the center, my molecules have a certain size and interaction, which means that the next molecule needs to have a little distance from me, which is where this dip happens. Nothing can be very close. And then, since it's packed, the next one is getting, a high probability of being at that distance, etc. This little, line basically gives us all the information we need in order to compute the 2-point correlation functions for this free energy. And then what we do is we do MG simulations. We get our densities at every grid point with a number of particles, let's say. We map it through a neural network. We do 2 times auto-diff, which gives us so we predict the free energy. We then take 2 times auto-diff to get the 2-point correlation function. We can compute the 2-point correlation function in theory as well, using this Ornstein-Zernicke theorem. And then we compare the two, and we minimize the difference. No external potentials, right? We're just looking at things which are flat, like a bulk. And we train this, and then once it's trained, we can now run this equation, which is called the Picard iteration, which is the same as the self-consistency loop in quantum DFT, which is you start with some initial density rho. You need the first derivative of the free energy with respect to rho, and then you run this to minimize basically omega, the graviton potential. So you now take a new situation, but with an external potential, you stick it in, compute the free energy, do 1 times auto-diff, get these derivatives, stick them in this equation and iterate. Okay, and so here's some one-dimensional examples where this is the true sort of density, and here the blue line is where you see it, it equilibrates under this process to find this equilibrium density. We can now do this in 3 dimensions as well, of course, using all the symmetries of the system. We can do this now in 3 dimensions very, very nicely as well. And so this got published in PRL very recently, if you're interested in reading more about this. But I find this what I find interesting about this example is that this was not a very popular method at all. Nobody used it. Why not? Because people couldn't write down the right functionals for the free energy. So they wrote down things which were based on cluster expansions or whatever, but they didn't really work well. When you use a neural net to train that thing, it can be much more expressive. And now suddenly this method's really started to work well. It's another example of where machine learning can really take something that didn't work very well and turn it into something that can actually work very well. By combining the strengths of both, I would say. Here's some more results. It's also very interesting, of course, that you can predict free energies directly in one shot. You don't have to go through complicated calculations. I'll just skip this for a moment because we're running a little bit out of time, I think. And so maybe to start sort of ending a little bit, I view we are sort of at the cusp of a golden age for material science. So a lot of people focus on ChatGPT and AGI and all these things, but I think the more interesting part, I'm sure all of you agree with me here, I think the more interesting part is actually applying these ideas to disrupt the field of materials and scientific computing. And of course, somewhat dramatically, we've named the ages in which humanity sort of evolved technology to the actual materials that they use, from stone, bronze, iron, plastic, possibly now to, I would think we're going to enter a phase where we do material on demand. You just tell me what material you want, there's a search engine, like you would now search for information, you can search for materials with those properties, even making sure things are being synthesizable, etc., and it will give you the answer. So that might dramatically accelerate the cycle of innovation. And it's, of course, the fact that we have these fields which are all around molecular science. These are old and mature fields where there's a lot of wisdom. These are much more young fields, like computational science. I've just heard you've got the biggest supercomputer here on site. That's computational science. Machine learning is adding to that now, fast, and changing the field. And of course, hopefully in the future, quantum computing can also be actually the first sensible application of quantum computing is, I think, to simulate quantum mechanics. And then there's all these applications which are, I think, real societal problems that need to be solved relatively fast around health, maybe resistant bacteria, antibiotics against resistant bacteria, or pandemics or whatever. Sustainability, getting carbon out of the atmosphere. Energy sector, batteries is a great example there, or hydrogen splitting, so hydrogen production using water splitting, etc. And so this is what we are building at COS, but the startup that I was talking about is basically a system that sort of is built on generative AI. It's a foundation model for generating molecules. It searches in the space of possible molecules, and it builds lots of property predictors to predict very quickly the properties or simulate the systems that are being predicted. All of that generates data that go back into a database in which we then improve our models and we accelerate this cycle further. And of course, there's a search engine around this thing which really tries to identify materials which are, which people want to use for certain applications. And so the last slide is, in my view, there is a deep connection building between AI and the natural sciences, and free energy is the core concept that we need to understand. And we can see lots of cross, fertilization. Machine learning is helping the sciences do simulations faster and better. But these concepts from science, including symmetries and free energies, but also things like fluctuation theorems, all these things that are coming out of non-equilibrium thermodynamics, they also start to bring new concepts to build better machine learning algorithms. And so you could argue machine learning is a new hammer for the scientists that will develop fast and be quite powerful. And then maybe the most important part is that there is lots of really important applications that can be solved with this in both health and sustainability, such as developing new drugs and new materials. And I'll end there to leave some space for questions.
Fascinating, very informal, excited by the results you have done, very thankful. Let's have a Q&A session. I do think there were hands raised up, but before we go into the online, is there any question from the audience in person? Yes.
So what you're saying is, let's say I want a material that captures carbon dioxide out of the sky and turns it into a solid material. Are you saying that if those are my parameters, you could create that material and put in as a parameter to make it the cheapest possible way possible? And
Yes. Well, okay.
how would you train a model?
Right. So you have to break the problem up a little bit. So let's say, the way we're looking for a certain set of materials called metal organic frameworks. So that's a class of materials. So you can train a foundation model for metal organic frameworks so that you can simulate them very fast. So then you can, and then you need to find the material, the metal organic framework that absorbs, let's say, carbon dioxide in natural atmosphere, so where there might also be a lot of water and other like nitrogen in there, but preferentially takes the carbon dioxide and binds it, and then also you need to model how it can be released without using too much energy. If you have a simulation pipeline for these processes, right? So you can, if I give you a material, you can quickly, using machine learning components, evaluate how good that material is for that entire process, which is, it could be complicated, right? Because it could be either simulating, the adsorption process with the machine learning force field, or maybe predicting like heated adsorption or other kind of properties or porosity or whatever of that material directly with property predictors. So with machine learning models, you can accelerate it. Once you have this ability to very quickly evaluate a material, you can then start building generative models that generate lots of candidates and then start to evaluate them quickly. And of course, what you really want is that when you generate these materials, you want not just random ones, you want the ones that are guided by your objective function, which is I want materials with these specific properties. And you can do this by either conditioning the model on that information, like a prompting if you wish, or guiding the generation in the direction where you think the interesting materials are. As the generative model gets better and better, it produces more and more sensible search results or molecules, which you still have to evaluate, but you sped that process up too by machine learning methods. Right? And then the cycle of going around accelerates faster and faster. So that's the whole process that's being built. And that's, of course, it's all about how do you do one step in that cycle, or going around one step very, very fast. Because once you have these candidates, you want to come up with a list of candidates and go to the lab and say, now, please synthesize these. Right? So you have to think about, are they actually even synthesizable? How expensive are they to synthesize? Are they actually good materials in the real world, which you also have to simulate? Can you actually put them in an actual machine? Will they remain stable, or will they disintegrate after a few cycles? All of these things will have to be simulated. But then you can optimize against it in silico, in your computer. And by the time you get to the lab, you say, now please synthesize these for me. You want a very high probability of success.
Right.
So otherwise you have to go to the lab way too many times and the cycle slows down a lot.
Yeah.
So that's kind of the process that we're pursuing. And I think it's a continuous process. It's not like you flip a coin, you flip a switch and then everything is perfect. It's something that continuously improves itself over time as more data becomes available, more experiments have been done. But it is something that can really accelerate the field with.
Yeah. So I was kind of interested, halfway through you talked about how we drop the physics from the model and we just train this solely on data.
Yeah.
It seems like, you're throwing out a lot of the fundamentals that you kind of know. I guess in some sense, I guess it seems like you're missing some of the physics and maybe you don't understand it. So how could you use that to basically have a model that performs better than your base understanding to increase it rather than just drive performance?
Yeah. So that's a great question, and that only works when you have a lot of data. So in the case where you don't have a lot of data, you want to put in a lot of sort of physics back into the model. But what happens for these weather prediction models, there's a lot of actual data out there that's not just generated by models, right? So there's actual data from the atmosphere, if you wish. So if you train your models both on predictions and from actual data, which is basically what people do. So they basically take these observations, which are of course very sparse, and then you kind of interpolate all that data using their simulators to create an initial state, let's say, for your model. And then they predict the future. That's the new state, and then again actual data, and then you correct it again using the actual data. So it's a combination of the simulation, which you think is an interpolation machine, and the actual data. Now you can see if you train your machine learning models on that combination, you can be better than the simulator. Because the simulator doesn't use the data, the actual observations. The simulator typically is the laws of physics, right? And you take the initial state is the actual state of the, let's say, it is obtained by using actual data, but then the actual predictions are used by just using an Navier-Stokes equation. These models, even in the way that they evolve the state, use the actual data and observations. And so they can actually be better in that sense. Now there is a danger to all of this as well, which is if you don't use laws of physics, you might get, when you get into new territory, like you've never seen a very, very hot place before, or maybe the CO2 levels are so high now, it's, that you have never seen it before, like when you do climate modeling, that you could run out of the regime where you've trained your models. And so reliability and uncertainty prediction are really key in this as well.
So you're basically bounding it with your physics and then fine-tuning with the actual data that you have?
Yeah, I think it can both ways. I think it's typically good. Okay, so here, the example is that people have now, so when you try to put in, let's say, symmetries, it seems completely sensical to put symmetries in, and this is what we've been doing for a long time, but people are starting to throw out symmetries when the data sets are very large. And the reason is, putting in all these constraints makes these models also harder to learn. And so they can actually, when you have a lot of data, the models that throw out all the physics are actually starting to perform better now, right? And so this is something to do with learning dynamics. I think the pendulum will swing back, and people will say, well, we can also put the physics back into in other ways and learn well. And so I think in the end, it's always a good idea to put in things like energy conservation, which you really want to hold in these models. And so there's certain things which we have to learn how to put back into these models. But right now, it's really, it's a battle between easy ways to train very, very large models and a lot of data versus trying to be smart with all sorts of physics information. And it's a function of how smart you are with training these models and how much data you have available.
Kevin?
Okay. Well, you made a connection between this machine learning and non-equilibrium thermodynamics.
Yeah.
I think it was very interesting to me. Do you think this, our knowledge or physics concept from the thermodynamics can help us understanding the theoretical background of the machine learning?
Yes.
For example, like convergence property of the neural networks. Something.
Yeah, so that's tricky though. So I think the field in physics which is related to the learning part is called control, right? So in fact, people do try to control physical systems to do certain things for them. So that's quite related to the learning part. But once you start messing with the system, it's not just physics anymore, right? It's like, it's like the learning part is less physical in a sense because you're trying to get something from a high entropy state to a low entropy state. And so that's less like around what is the theory of physics that can help you. The other direction, of course, is exactly physics, but that's actually in these diffusion models, just an Uhlenbeck-Ornstein process. And it's built very well understood. However, one direction in which we are going is to think about, could you, for instance, in the forward process, an Ornstein-Uhlenbeck process, it takes infinitely long to get to a Gaussian distribution, where we really want this into a finite number of steps. This is to happen in a finite number of steps because of the computational resources you have. And so now there is there's very interesting work which is called like optimal transport, where you can show how to bring one distribution to another distribution in a finite amount of time. But you have to apply forces again, so it's more like a control system. And then the hope could be, you could show, by the way, that process dissipates the minimum amount of work. It's the most efficient way physically to say change the distribution into another distribution. Or it's also called counter-diabetic driving. So now you could hope that this theory, which tells you something about dissipation, work dissipation, and heat generation and whatever, is related to, let's say, variance properties of estimators. And that's actually true. So it's actually true that if you take, so where does heat generation come from in thermodynamics? It comes from fluctuations. Right? So if you have the least number of fluctuations, in fact, what will happen is that you generate the least amount of heat. So these fluctuations you can show will cause variance in certain estimators, let's say of free energy differences between two states. So there's a direct relationship between estimation, statistical estimation, and some physics process. And now you can start to learn. You can say, okay, what did people do in physics to control systems to have minimum heat generation? Could we use those and the theory around those to help us design better statistical estimators and better learning algorithms?
Thank you. There are I'm sure there are more questions, and also there are indeed questions from online, but we do have a next schedule to cover, so unfortunately we have to end it right now, but let me propose something. Max is going to stay here on site the whole afternoon in this room actually. So if you have want to have a more detailed discussion with Max, I welcome you to come by starting from 1 p.m. Throughout the whole afternoon. So please come here. And for the participants online, if you would like to engage in the afternoon sessions, please let me know so that I can send the WebEx the invitation so that you can come and then engage in the discussions as well. So shall we do that?
Yeah, sounds good to me.
Okay, well, for the last closing remark, let's thank our speaker today.